In the kitchen, the refrigerator is a marvel of physics that seems to defy the laws of nature. We think of it as a machine that creates cold, but in reality, it is a machine that moves heat. Deep within its insulated walls, a complex dance of thermodynamics takes place, shifting thermal energy from the food inside to the air outside. To understand how it works, we must look at the four critical components that make this impossible feat possible: the compressor, the condenser, the expansion valve, and the evaporator. Together, they form a sealed circulatory system filled with a specialized chemical called a refrigerant. This substance has a unique property. It can boil at temperatures far below freezing, allowing it to absorb heat even from a cold interior. Imagine trying to boil water with an ice cube. That is the level of precision engineering we are dealing with. In this journey, we will follow the refrigerant through its transformation from a low-pressure gas to a high-pressure liquid, and back again, all to keep your groceries at a steady, crisp 37 degrees Fahrenheit. This is the engineering of the invisible, where pressure and temperature are manipulated to create a sanctuary of preservation within a world of ambient warmth. Every refrigerator has a heartbeat, and it sounds like a low hum. This is the compressor, a powerful pump located at the bottom of the unit. Its job is simple, yet brutal. It takes in cold, low-pressure refrigerant gas and squeezes it. Inside the compressor's steel shell, a piston driven by an electric motor moves at high speed, compressing the gas into a fraction of its original volume. As the molecules are forced closer together, their kinetic energy skyrockets. This causes the temperature of the gas to rise dramatically, reaching over 120 degrees Fahrenheit. This is the work part of the thermodynamic cycle. By increasing the pressure, the compressor sets the stage for heat rejection. Without this pressure jump, the heat inside the fridge would have nowhere to go. The engineering tolerances here are microscopic, with the piston fitting so tightly that it requires a constant bath of specialized synthetic oil to prevent friction from melting the metal components. It is a high-pressure environment, designed to run for decades without a single failure, pushing the energized gas forward into the next phase of its journey, the cooling coils. As the hot, high-pressure gas leaves the compressor, it enters a long, winding maze of copper or aluminum tubing known as the condenser coils. You can usually feel the warmth radiating from the back or bottom of your fridge. That is the heat that used to be inside your leftover pizza. As the gas flows through these coils, it encounters the cooler air of the room. This temperature difference causes the heat to migrate, flowing out of the metal tubes and into the kitchen. As the gas loses this thermal energy, it undergoes a phase change, condensing back into a liquid. This liquid is still under immense pressure, but it is now much cooler than it was when it left the compressor. The design of these coils is critical. They are often fitted with thin metal fins, much like a car radiator, to increase the surface area and maximize heat transfer. It is a passive process, but a vital one. If the coils become covered in dust, the heat cannot escape, and the entire system loses efficiency, forcing the compressor to work harder and shortening its lifespan. By the time the refrigerant reaches the end of the condenser, it is a high-pressure liquid, ready for the most dramatic transformation in the cycle. The high-pressure liquid refrigerant is now standing at a closed door. This door is the expansion valve, or in many home units, a tiny, hair-thin tube called a capillary. This is the bottleneck of the system. On one side, we have high pressure, on the other, a sudden drop to low pressure. As the liquid is forced through this narrow opening into a wider pipe, it experiences a phenomenon known as the Joule-Thomson effect. Think of it like an aerosol spray can. As the liquid expands into a gas, it turns freezing cold. This sudden expansion causes about half of the liquid to instantly flash into a vapor, a process that consumes an enormous amount of energy. This energy is pulled from the refrigerant itself, causing its temperature to plummet to roughly -20 degrees Fahrenheit. In a fraction of a second, the refrigerant has transformed from a warm liquid into a frigid mist of liquid and gas. This is the cold that will soon enter your refrigerator's interior. The precision of this valve is paramount. If the opening is even a fraction of a millimeter too wide, the pressure drop won't be sufficient and the fridge will fail to stay cold. It is the gatekeeper of the cooling process, controlling the flow with surgical accuracy. Now, the frigid refrigerant enters the evaporator coils, located deep inside the freezer or refrigerator compartment. This is where the magic happens. A fan blows the relatively warm air from inside the fridge over these ice-cold coils. Because heat always moves from hot to cold, the thermal energy in your food and drinks is sucked into the refrigerant. As the refrigerant absorbs this heat, the remaining liquid droplets boil away, turning completely back into a gas. This phase change from liquid to gas is the secret to modern refrigeration. It allows the system to absorb a massive amount of heat without changing temperature itself, a process known as latent heat. This is why the air coming out of your vents feels so sharp and cold. The engineering challenge here is managing frost. If moisture from the air turns to ice on these coils, it acts as an insulator, preventing heat from being absorbed. That is why modern fridges have defrost heaters, tiny electric elements that melt ice away every few hours, ensuring the evaporator can continue its job of stripping heat away from your groceries 24 hours a day. A refrigerator is only as good as its envelope. To keep the cold in and the heat out, the cabinet is a sandwich of advanced materials. The outer shell is usually cold-rolled steel, often coated in a powder finish for durability. Inside, a liner of high-impact polystyrene provides a clean, food-safe surface. But the real hero is the layer in between, pressurized polyurethane foam. This foam is injected as a liquid, expanding to fill every nook and cranny before hardening into a rigid, insulating barrier. This insulation is so effective that even if the power goes out, a well-sealed fridge can keep food safe for hours. Scientists and engineers have spent decades perfecting this foam, ensuring it has the lowest possible thermal conductivity. Then there are the gaskets, the rubber seals around the door. These contain flexible magnets that pull the door shut, creating an airtight seal. Without this, warm room air would leak in, bringing moisture and heat that would overwhelm the system. Every material is chosen for its ability to resist the constant stress of temperature cycles, ensuring the machine can maintain a 60-degree temperature difference from the kitchen to the freezer for 15 years or more. Modern refrigeration isn't just about plumbing, it's about intelligence. A network of thermistors, or temperature sensors, constantly monitors the internal climate. These sensors are so sensitive, they can detect the slight rise in temperature when you put a warm bowl of soup inside. This data is fed to a central control board, the brain of the appliance. In older models, the compressor was either on or off, but today, many fridges use inverter compressors. These can vary their speed, running at a low, quiet hum to maintain temperature, or ramping up to high speed for a power cool after a grocery trip. This precision control reduces energy consumption by up to 30%. The brain also manages the defrost cycle, the ice maker, and the airflow between the freezer and the fridge via motorized dampers. It is a balancing act of physics and software, ensuring that while the freezer stays at 0 degrees, the lettuce in the vegetable crisper remains at 38, never freezing and never wilting. This electronic oversight ensures that the thermal dance remains perfectly choreographed day and night. Before a refrigerator can ever enter a home, it must survive the gauntlet. In testing labs, units are placed in hot rooms reaching over 110 degrees Fahrenheit with 95% humidity. They are expected to maintain freezing temperatures inside even when the environment is oppressive. Robotic arms open and close the doors over 300,000 times, simulating decades of use by a hungry family. Technicians use ultrasonic leak detectors to ensure that not a single gram of refrigerant gas escapes the hermetically sealed pipes. If a leak occurs, the system fails and the environment is harmed. The compressor is subjected to voltage spikes and rapid-fire starts to ensure its electrical windings can handle real-world power grids. Only after passing these brutal torture tests does the unit receive its certification. It is a testament to industrial engineering that a machine this complex, involving high pressure, chemical phase changes, and sensitive electronics, is one of the most reliable appliances in human history. It is a silent sentinel, working tirelessly to move heat, keeping our food safe and our lives convenient. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.